Hallo und guten Tag zusammen. Mein Name ist Florian Wohlrab. I'm a RISC-V ambassador and I'm also sales manager for Andes Technology. It's my pleasure to be here today on this first RISC-V meetup in Duisburg. It's very amazing to be here and have my presentation. I hope you can see the presentation now in the background. And today I want to talk about RISC-V SoC architecture and exploration for AI and machine learning. Which age are we in right now? Well, John Hennessy and David Patterson, which received the Turing Award, have been both working on this RISC-V architectures for ages. And I would say there are kind of four pillars which we are having or which we are seeing right now today. The first is domain-specific architecture. So that means people want to develop a SoC or people want to develop a processor and they want to add their own instruction, their own secret source or their own recipe for speeding up things. Another thing is security. What we are seeing is that today in our always connected, always on world, security is becoming more important. Everyone is trying to hack things which are on the internet connected all the time. So security is more and more important. And then agile hardware development. That means you're developing a SoC and you don't have 4 years to finish it. No, you only have half a year or 1 year to finish it. That means you need to take more components, off-the-shelf ready components, combine them. You need to speed up your development and everything. And then last but not least, open ISA. Yes, we are in the age of open instruction set architectures. And that is amazing because many people have been waiting for this, to have an open ISA. Everyone can make his own implementation and speed it up. So to make it short, we are today in the age of the golden computer architecture. We are defining the next computer architecture right now. And that is very amazing. And I'm very happy to be here with you together. Open RISC-V architecture is perfect fit for this. Why? The Open RISC architecture is inspired by the success of open software, for example, like Linux. You can think about it like a Linux for processors. It allows people to contribute together, to share ideas, and to make the next successful hardware for chips this time. Having more people working on RISC-V is great, because it drives innovation. It makes innovation happening much faster. People with great ideas just can go out and build them and modify and test them. And then last but not least, this open ISA allows for incredible ecosystem support. Many people are motivated by the openness and contributing, helping to maintain, improve, and contribute their own ideas. So incredible ecosystem support will drive further adoption and make many more people working on it. How is it focused around RISC-V? Let's have a look. RISC-V itself is coming from academic research, so it's driven by academics and researchers, but today we also have commercial companies like Andes Technology, where I'm working, and many more, and we have people who making it open source and making their own cores, sharing them with everyone like Linux. And then on top of this, you have all this innovation where you have semi-IPs using it. You have design services building on RISC-V, but you also have chip vendors bringing out devices with RISC-V so people can buy ready-to-use devices and then build software on top of it, cloud software or machine learning algorithm to speed it up and to innovate it and to bring it more. Let me share a little bit how, because Andes, we are a commercial provider, but actually because we believe in RISC-V a lot, we are also very active in RISC-V. So our roles, for example, our president, our biggest boss, Frank Lin, he's a RISC-V board member and is actively contributing his time, helping to steer it in the right direction for open source. Then we have our CTO, Dr. Charlie Su. He's a vice chair and he is also heading a technical steering committee. Like, for example, we are working in the DSP and vector interrupt controllers, things like this. And then there is also myself. I'm a RISC-V ambassador. However, I'm also a sales for Andes. So just to show you, even we are a commercial company, we are working very hard to contribute to the RISC-V. Before we jump into SoC architecture, just let me give you a very brief overview about Andes, who we are. So Andes is a Taiwanese company, and we are a pure play CPU IP company. So that means we are developing CPU IP based on RISC-V, and we are selling it to our customers. That's our business. Before RISC-V, we had our own RISC architecture, but now it's purely RISC-V. We are also a founding member of the RISC-V Foundation, now RISC-V Association, and we are a premier member as well. We're also the first company in Asia to be a pure CPU play company listed on a stock exchange. So we are listed on the Taiwan Stock Exchange. And in RISC-V, we are running multiple task groups, but also contributing to open source like U-Boot, GCC, LLVM. You will find our engineers contributing our code enhancements and improvements. So yeah, we are very active in this. Some quick facts about Andes. We're a 15-year-old company, and we have worldwide around 200 licenses. So that means quite a big customer base. Because we're focusing on CPU IP, the majority of our people are R&D employees. And a milestone which we are very proud of is 5 billion accumulated Andes embedded SoC shipments. So our customers have shipped over 5 billion devices with our SoC inside. And then we are also having our own integrated development environment where we have a worldwide installation base of 17K. Like I said, we are a Taiwanese company, so our headquarters is in Taiwan. We have offices in Shanghai and Beijing, but we also have people in Korea and Japan. We do have actually 2 offices in the United States, and we have people in Israel, France, and Netherlands. So if you're from Europe, Germany, and you have a request for us, we will have a local guy next to your door. Let's have some more deep look in the RISC-V. What is the market adoption and some usage examples? Because we said, how do you scale it from very edge to high end with Linux? So first, the momentum has kind of changed. When RISC-V started, RISC-V was in the deeply embedded section because it was cost affordable, it was quick to implement, it was easy, it was a small core, so it was not a big logic, not very complicated. That's why it find stronghold in like offloading infinity state machines or replacing them with a small microcontroller, but also housekeeping tasks like managing your SoC. And then there also has the DSP capability, I talk later about this, which have helped to push RISC-V in this deeply embedded application. But what we are seeing today is that RISC-V is pushing more and more in the previously ARM-dominated areas. So talking about general purpose microcontroller units, which can run Linux or even smartphone processors. We are seeing RISC-V is gaining more and more stronghold about this and pushing more in this, pushing ARM more out to the very high end. Let's have some examples. Actually, that's a real product. One of our customers made this product. So he was using our core D25F. I will have some details on the D25F later. And our customers made a chip for true wireless earbuds and hearing aids. The chip is already taped out and we do have the approval to talk about this. So the customer used our chip, the D25, like I said, and he was also using the RISC-V DSP extension inside to accelerate some of the noise and echo cancellation algorithms, but also to add some support for machine learning for keyword spotting, like, for example, hey AirPod, volume up, or hey earbud, volume down, something like this. The SoC actually is also doing partly the Bluetooth codec and the LC3 codec, like for the audio codec coming in. If you're looking for some example, for a more abstracted example, how you can build a SoC today, for example, for edge computing with vision processing, then what we can see is that you will have a core which might be, like in this case, Andes A25 multiprocessor. So you don't have only one core, you have multiple cores with an L2 cache capable running Linux, mostly a stripped down Linux. So it's not like a Debian distri. It is really optimized for the core. And this is doing the management of the core. And then you will have your image processing where the images come in, for example, from a camera. And this core will do the image processing, translate it to the right formats, translate it to a video codec or something like this. And that can use a different core. So for example, here I wrote an NX27V. So that, for example, might run a real-time operating system like FreeRTOS to do all this data management and be managed by the control core. And then last but not least, you can also add a neural network processing unit. And in this, you can have one vector processor. You could have multiple processors together with an accelerator. And that could do things like detecting what is in your picture. For example, detecting if there is a dog inside or if there is a car inside. That's an artificial intelligence algorithm where you can have a dedicated neural network processing to offload your main CPU and to do this more power efficiency dedicated. All of this would be connected by a network on chip. Today, the industry standard is like AXI bus. There are some other open source or open standard buses like Tielink. We are watching this very excited and very closely, but for an industry device today, AXI is still kind of standard. Let's have a look in a data center. What would you do for a data center accelerator? So for a data center accelerator, you see it looks very similar. You have again a main CPU which would run some stripped down Linux version, doing the handling with the interfaces, like for example, PCI Express to the outside. And then you would have some data processing units like a vector processor. Not only one, you would have maybe multiple in this. And the main CPU would take the data from the outside, coordinate it, and forward it to the vector processing. Think about Bitcoin mining, for example. You will get in your input, what is the hash you have to calculate, and then this main CPU would distribute it on the different vector processor, let them do the number crunching, and once the number crunching is done, the vector processor give it back to the main CPU. The main CPU will feed it back to the network. Additionally, what we see is also you can add some neural processing. Again, why I'm showing you this is kind of redundant, but that's actually a real-world implementation where we see that people adding a controller CPU with a dedicated accelerator. Coming back to the Bitcoin mining, for example, you would have some hardware accelerator who is only doing the hash calculation or the hash crunching, and this would be controlled by a core like the NX27, but this core can control many of these accelerators, not only one, maybe 4, maybe 8, maybe 16. And what this core does, it just control it and it gets its job from some other control or coordination core and just forward it. So by this, the accelerator is very dedicated, but you still have a programmable logic inside, making it more versatile, more future-proof because you easily can upgrade. RISC-V, added value and contributed extension. If RISC-V is an open instruction set architecture, why do you have commercial vendors like Andes offering it? Well, we are adding value to it. For example, we are adding some baseline ISA extension to speed up memory access and branches, which comes from our know-how. We also have things to reduce the code size even more, some clever hardware mechanism inside the core. And we're adding more functionality like power break, which can help you to stall the pipeline and save energy. We have stack safe for hardware protection. We have vectorized platform level interrupt controller for a more preemptive behavior of a real-time operating system. By the way, this vectorized interrupt controller, we are also contributing back to RISC-V. So we are sharing it with the community. We feedback what we see the market need, what the commercial people need, and we're making this information available to everyone. So we are not just benefiting of RISC-V, we are helping RISC-V to grow. And especially if you want to make a commercial chip, if you want to make 1 million chips, you cannot have a mistake inside. So that's also something Andes is guaranteeing. We're doing the verification of the chip. We guarantee everything is working. We give you the support for design in. We give you the support if you integrate it with something else. And that's one of the benefits. So I think open source is very important. And also if you go in commercial, some may use open source, but you would be surprised the majority of customers is using offers from companies like Andes. Something more Andes has provided, that is the DSP extension. Actually, that is to accelerate slow video, audio, voice, and low data workloads. For example, unlocking a door frame or unlocking your mobile phone by looking in the camera. That has slow data rates like 3-5 frames per second, or making an audio codec or keyword spotting where you are always listening for the keyword like, hey, device, wake up. That needs low data rates, and third is SIMD instruction really can save power. Andes has developed this for our proprietary cores previously, but when RISC-V came and we joined RISC-V, we saw that was missing and we have contributed it to RISC-V. So we gave our SIMD DSP ISA to the RISC-V community. We make a committee where we are discussing with all the other vendors from academia, from commercial, and also open source can join. We are discussing and making it an official standard so it's supported by everyone. Just to show you some numbers why it is good, for example, the keyword spotting I said, it can speed up by 5.2 times, but the speed up also means that you can run it slower. So for example, if your CPU runs at 500 megahertz and needs a lot of energy to make the keyword spotting, with the DSP extension, you can clock down to 100 megahertz and still have the same throughput, but save more energy. Especially if you're talking about devices powered on a battery, that is a very important feature. And then last but not least, the domain-specific architecture, which allows you to add custom extension to RISC-V, is very important. That's one of the main differentiator in RISC-V, where customers can add their own custom extension. And here Andes is providing a tool, we call it Copilot. It's like an EDA tool. It takes the input from the customer, like your hardware module in Verilog or HDL, and it is then integrating it with the processor pipeline, so saving you a lot of work. You can do this by yourself, but if you integrate it in a pipeline, if you touch it, you need to verify the whole processor again. So again, if you want to tape out and you go 1 million chips or something, you cannot have a mistake inside. And that's where EDA tools like this can help you a lot. Then last but not least, the roadmap from Andes. I will go very quick over it just so you know we have a roadmap and we have an impressive lineup. We are ranging from a 2-stage core, over 5-stage cores, up to 8 stages. And this then goes from the left side from fast and compact cores, which you would use in a microcontroller unit, over adding the DSP extension for something like Bluetooth. And then when you want to run Linux, you will need like a memory management unit, and it ranges up to cache coherence multi-cores. That would be, for example, the 45 multiprocessor where we're adding L1 and IO coherence as well as L2 cache. One thing I got questions a lot, people say, hey, only 1.2 gigahertz, that's not much. Well, actually, I think it's a lot. And secondly, all these numbers are worst case numbers on TSMC 28 HPC plus. So that means if you have plus 85 degrees or something like this, if you have really stress on your system and bad voltage, then you still will reach 1.2 gigahertz. If you have perfect condition, if you have lower temperature and everything, it will run much faster. Very quickly about the vector series, which is a gray style scalable vector processor in it. So why should you use it? First, because it's from RISC-V. It's an extension, the vector extension. It is open, so you can add it. Then Andes has done some clever extension for it, like we are adding bfloat 16 and in 4 data types. It is scalable, so you can implement it ranging from a microcontroller unit up to a supercomputer, and the performance increasement is huge. Also, efficiency is better with the vector processor because it can help you to process more data in a shorter time. And then last but not least, Andes has provided some nice tool which helps you to analyze your pipeline and make it more clear. Here's some picture from how we integrated the vector processor. So we took our kind of standard core from the 27 series. You see you have an instruction fetch, then you have the decoding phase, and after the execution unit, like the first integer execution unit, the instructions will be forwarded to the vector processing unit, which then will do the heavy number crunching, the calculation. What we are seeing is that it's very low power. We have added some things like multi-level clock gating, in order, one read write, SRAM cell based. And if you integrate, for example, 50 of this vector processing units in one SoC, you can build a open compute card, which is below 10 watts. By the way, the RISC-V vector is right now at the version 0.9, I think. Our first integration was 0.8, and we are updating now to the 0.9. So there is also some service, like if you make a RISC-V, and there are some things which are not yet ratified, which are still changing. Some vendor like Andes Technology will support our customers and will provide them the latest updated specifications, and also help our customers to update their SoC design if there is something updated in the spec. Then some overview. I will go very quickly over it. Here I just choose the 25 series. That is a 5-stage pipeline, single issue. It has configurable multiplier, so you can configure it for very fast and a lot of die area, or for more slow and less die area. It has instruction data caches and local memory. There's optional parity or ECC protection. And the bus interface, you can choose to have AXI or AHP. Now, the interesting thing is, SETC is good to run a real-time operating system, but if you want to run a Linux system, what can you do? So what we are doing is, we are adding this one core, which you see on the left side, and we are putting it multiple times inside. In this case, up to 4 times. We have the platform level interrupt controller, who is providing the interrupts for all of the up to 4 cores. We have the debug support over JTAG, which is adding or let you trace and debug all the cores. And then we are adding also a Andes coherence unit, which is making sure that you can add an L2 cache controller and making sure that the data between the cores coherent. So this course here inside has the A versions. That means there is a memory management unit inside, and that would be perfect to run a Linux system. The bus interface here you can see is 128-bit. That reflects that you will have a higher data throughput, and then you need to have a more powerful connection to your bus. And this is also providing some platform, like you can see here. So normally we are a CPU vendor, but some customers who know what they do, what they want to do, ask us to also provide a platform. So we have some simple bus metrics. We have some like GPIOs, quad SPI, I2C, UARTs, and so on, and also some DMA we are providing to our customers. Our latest core, just very quickly, is the 45 series. That's the 8-stage in order dual issue. Dual issue means you can put 2 instructions inside at the same time. What is interesting, you have here 2 sets of arithmetic logical units. So that means if the first instruction needs to do some calculation, and the second instruction depends on the result from the first instruction. The first instruction could use ALU0, for example, do the calculation, and then the second instruction could use the ALU3 do the calculation and finish in the same cycle, and both instructions retire at the same time. So that is also pretty nice design. And that actually is something for what you would find as a CPU in a mid-range smartphone. Time to market, how Andes helps people time to market. So we provide our customers the whole set. We have an integrated development environment that is based on Eclipse. It has a lot of plugins which we have developed over time, like analyzing your program, profiling it for bottlenecks or things like this. It integrates with the FPGA boards from Andes, which help our customer to prototype the SoCs in a very fast way. And it also is connecting to this FPGA boards over our Andes debugging hardware, which is USB to JTAG basically. So it sounds very simple, but just providing our customers everything from one hand, making sure it works together, can help with a lot of time in development. Then we also provide our software stack, for example, Linux BSPs or different flavors of real-time operating systems like FreeRTOS, but also others. And we have bare metal demo projects like how to toggle a GPIO, how to use the local memories, how to control the watchdog timer. While we are trying to upload and push everything to the open source, like our Linux, our real-time operating systems, we are still making the BSP and provide to our customers. So what I said, you get everything from one hand, everything works together. Our customers save a lot of time if they don't need to find all the source code themselves on Linux. Some like it, some like to find it themselves on open source. We are supporting both. So that brings me to the end of my talk. And I hope I could show you that there is a strong ecosystem built around RISC-V. There is more and more technology and innovation contributed by a lot of people, not only Andes, but also by the academic colleagues, by people who are doing it for open source. And RISC-V we see is keep evolving through this collaboration of the community. So I want to invite you. I hope you're joining RISC-V. I hope you're signing up for a membership, or you're just checking out one of the open cores for RISC-V and you're trying to fiddle around, making your own, or just study RISC-V. And once you're working in a company, make it a product with RISC-V, because that will help to innovate, to spread and accelerate the growth of RISC-V. Andes, yeah, at the moment we are the only one to our knowledge who is providing all three extensions like P, Vector and custom extension framework together to accelerate AI. So that is, talk with us. And what we believe is that the commercialization of RISC-V, so having people who really integrate it into product, will accelerate RISC-V. And that's why we are so happy to share our ideas, share our contribution, because it will help the RISC-V and it will also help us as a company. So please join RISC-V and work with Andes. Okay, thank you very much for your time. I would be online now for some Q&A. So if you have your questions, feel free to ask me. And thank you very much to Alexander for organizing this. It was a pleasure to be on the first RISC-V meetup in Duisburg. All right, I'm open for your questions.